So, we are here this evening to celebrate the 200-year anniversary of Michael Faraday isolating benzene from whale oil right here at the Royal Institution. Now, benzene is a small 6-membered ring molecule. You can see it right here on the screen. 6 carbons in a ring, each attached to a hydrogen atom. Now, the discovery of benzene has led to inventions and industries that have completely changed our modern lives today, from synthetic dyes to plastics to pharmaceuticals and also advanced organic materials. Now, what I would like to do today is that I would first like to tell you the story of Michael Faraday. How did the son of a blacksmith, someone with very little formal education, go on to become one of the most celebrated scientists in history? And then we will explore the story of benzene, and towards the end of my talk, I'll tell you a little bit about some modern research on the topic of aromaticity. So let the story begin. Our story today starts right in the heart of Marylebone, London. Now, if you walk down Blandford Street 40 to House 48, which I did yesterday, you're going to come across this building with a plaque on it. Now, this building today is a sandwich shop, but in the early 1800s, it's actually a bookbinding shop, and this is the shop, this is the plaque that documents the humble beginnings of Michael Faraday, who was here as a bookbinder apprentice for 7 years. Now, Michael Faraday was the third of 4 children born to a poor blacksmith family right here in London. And so he had some basic education, so he learned to read and to write, do some basic math. But when he was 13, he had to quit school, drop out of school, and start to work to help his parents make ends meet. And so through his father's connection, Michael Faraday came to work for a man named George Ribow. Now, George Ribow is a bookbinder, and he needed an errand boy, someone to help pass out newspapers. And so that became Michael Faraday's first job, a newspaper boy. And so he would go out in the morning, pass out the newspapers to all the customers, and then he'll go out again in the afternoon to take back all of the newspapers and pass them out again to a separate set of customers who were willing to pay a little bit less and read the news a little bit later in the day. And so that's how boys worked during those days. Now, George Ribow found that Michael Faraday was a very diligent young boy. He worked very hard, and so he suggested to Michael Faraday that perhaps he would teach him the art of bookbinding. And so Michael Faraday came to this Blandford Street, House 48, and became a bookbinder apprentice there for the first 7 years since he turned 14, I guess. So, as we often see and we often hear that behind every hero, there is often an unsung hero. And I think that in many ways, that person for Michael Faraday was George Ribow. Now here you can see a picture of what Ribow's shop might have looked like in the early 1800s. Now Ribow was a very kind person, and he was very generous. He saw how Michael Faraday was a very bright and curious young boy, and so he encouraged that. He let him read all of the books in his shop. He let him read any of the books that came for bookbinding. He even let him attend scientific meetings, which he was very interested in, after hours. And this was very rare for apprentices at the time, because at that time, the apprentices usually had to stay in the shop after hours. He also let Michael Faraday do some experiments in the back of the shop. So you see, even though Michael Faraday did not have a lot of formal education, his time at the Ribow shop was very enriching. He had a very enriching learning environment. Now, during this time, Michael Faraday also acquired 2 important characteristics, which I think contributed why he became such a remarkable scientist. 1 is good hands, 2 is good observation skills. So during those times, in the early 19th century, as a bookbinder apprentice, you would be using all sorts of instruments every day. You start working at 6 a.m. until 6 p.m., and you will use all kinds of instruments to press the books, to cut the paper, and to stitch the pages together. And so from all this training over 7 years, he became very good with his hands. Second, he had very good observation skills. So during this time, there was actually a portrait artist named Jean Mascarrière who was sheltering under Ribau's shop. So he fled Paris from the Napoleon Wars and was living there. And he taught Michael Faraday how to draw. And for anyone who tried to draw before, you know that drawing requires a lot of observation skills. And so there you have it, the 7 years he spent at the Ribau shop. He read broadly, he was very in touch with many of the current scientific ideas of the time, and he also gained good hands and good observation skills. Now here you see a picture of Ribau showing off Faraday's invention to a customer. Okay, now Faraday had a very interesting hobby. As a young man, he really liked to take notes, and as a bookbinder, he could bind blank notebooks for himself, which is what he would do. So here you see a blank notebook. It's not blank anymore, but he bound a blank notebook, and he called it the Philosophical Miscellany. And if you can read the fine print there, it says, a collection of notices, occurrences, events, relating to the arts and sciences. And so you see here, you get a glimpse of his curious nature and his observant nature. He would make notes of anything he read, he heard, or he thought about in this notebook. And so from here you see you get a glimpse of the person behind, the human behind the scientist. Here you also see that a lot of times his notes would be completed with some illustrations. Here you see a picture of the electric fish that Faraday drew. Here you also see an illustration of how to prepare oxygen gas. So he really liked to take notes, and it's often completed with a lot of illustrations in this notebook. Now, during this time, during his 7 years at the Ribau shop, there was a particular book that impacted Faraday's interest in chemistry, and it was a book that he found in the bookshop called The Conversations on Chemistry. And if you take a close look at the bottom, you will see that this was written by a lady Marcet, Jane Marcet. So Jane Marcet was a wife of a Swiss exile physician. And like a lot of the upper-class educated people of the time, the Marcets would attend public scientific lectures. And so Mrs. Marcet would often go to these lectures, and she would come home and try the experiments in their own home laboratory. But at some point, she realized that even though she could replicate these experiments, a lot of the ladies that came to the lectures couldn't quite understand the chemistry or the interesting science behind the lectures. And remember, this was a time when not many women got the opportunity to have scientific education. And so Mrs. Marcet, being ahead of her time, she really thought that women should and could engage in complex scientific discussions. And so she set out to write this book for the ladies. Now, this book actually is written in a conversation style. It's written between a conversation between a Mrs. B, the teacher, and two students, Emily and Caroline. So this was actually perfect for Faraday because it was written in a very easy to understand way, and it's also completed with a lot of experiments that you could try out on your own at home. And here in this excerpt, you can see Michael Faraday reflecting the effect of this, the impact of this book on his interest in chemistry. He says here, when I came to know Mrs. Marcet personally, how often I cast my thoughts backward, delighting to connect the past and the present, and how often when sending a paper to her as a thank you offering, I thought of my first instructress. So he actually later met Mrs. Marcet when he was on a tour in Europe. Now that story comes later, which is now. So towards the end of the 7 years that Michael Faraday was a bookbinder apprentice, a series of events happened, and that opened a path to science for him. At that time, the most powerful chemist in London was a man named Sir Humphry Davy. So Humphry Davy, you can see some of the exhibits downstairs in the museum with some of his work there. So Sir Humphry Davy is known for several things. He's known for discovering several elements by electrolysis. He discovered laughing gas, nitrous oxide, which is N2O. He also is known to invent the Davy lamp, which added a layer of mesh on the lamps that coal miners used to prevent explosion. So at this time, Davy Humphrey was the professor of chemistry right here at the Royal Institution, a very powerful chemist. Now, this powerful chemist married an extremely wealthy widow named Jane Aprice. And so he thought that after getting married, he's going to stop giving public lectures. And as a last bow out to the public audience, he decides to give a last 4 lectures. Now, these tickets were sold everywhere, and everybody wanted to come see Sir Humphrey Davy speak, including Faraday, who could not afford the tickets. But at this time, a regular customer at the Ribau shop, a gentleman named William Dance, he knew Faraday, and he knew that Faraday would really enjoy these lectures. And so he decided to buy the 4 tickets, and he gave them to Michael Faraday as a gift so that he could attend these lectures. Now you see, Michael Faraday loved to take notes, and he is a bookbinder. And so he bound a blank notebook again and brought it with him to Sir Humphrey Davy's lectures, and he took copious notes, everything he heard of and he thought about, he put them down in these notes, and eventually he actually sent this bound book of notes to Sir Humphrey Davy, and that eventually led to a position with Sir Humphrey Davy as his assistant right here at the Royal Institution. Now, working for Davy opened a lot of opportunities for Faraday. By then, the bookbinding career is behind him, and his whole scientific career is in front of him. So right now, he can now work on the science that he loves, and he also got to meet a lot of the most influential scientists of the time. Now, during this time, so this is actually at the height of the Napoleon Wars. And during this time, Napoleon Bonaparte actually created what was called the Volta Medal, the Volta Prize and the Volta Medals. And the medals were to be awarded to any scientist, any international scientist that had made significant contributions to the study of electricity. And Sir Humphrey Davy was awarded this medal, so he was scheduled to go to France to receive this medal. This was about a 30,000 franc medal, which translated today is about £250,000 to £500,000. So Sir Humphrey Davy was about to go receive this medal, and Michael Faraday got to go with him to Europe. And during this trip, he got to meet all sorts of influential scientists, including Ampere, which is the unit we use today for electric current. He also got to meet Alessandro Volta, and Volt is the unit that we use today for measuring electric voltage. And Volta was also known to have said at one point that we admire Davy, but we love Faraday. Because Faraday also was known, beyond being a brilliant scientist, he was also a very likable person with a very humble character. Now, upon returning to the Royal Institution, so Faraday was in Europe for 2 years. Upon returning to the Royal Institution, this was about in 1815. From there on, the next 10 to 15 years was when Michael Faraday made all of his most important discoveries right here at the Royal Institution. First, the electric motor, then the electric generator, and right in the middle, 1825, the discovery of benzene. So by this time, Michael Faraday already was a director of laboratories. He said he has already been in the Royal Institution for 12 years. And so this meant research freedom, which is important because that means he could work on whatever topic that interested him. And so he actually worked on a lot of public projects as well as commission projects with different companies. But at this time, a specific procedure caught his eye, and that was the production of portable gas by whale oil. So by 1825, the streets of London and most of the major cities in Europe were already equipped with gas pipes and gas lighting. Here you see a picture of a home in New York, and here you actually see 2 different light fixtures, right? One is attached to the wall, and the other is a lamp right there. And you see the one with that's attached to the wall, there's little arms that comes out. So that's attached to the back of the wall where there are gas pipes running through, and that's where the gas pipes carry through flammable gases, and they go through the arms and you come out mixing with oxygen, and that produces light. Now, the one on the table obviously is not connected to the wall, and you need a fuel for that. And so the fuel for that is actually a pressurized canister, and companies like the Portable Gas Company of London would produce these pressurized canisters by whale oil. So what they would do is that they would take whale oil, drop it in a hot furnace at a high pressure in the absence of oxygen, and that breaks down the whale oil, and from there you can get some flammable gases such as hydrogen, methane, ethylene, acetylene, and so on. And so Faraday noticed that during this process, an oily byproduct would be produced, and he became very interested. He became very curious in what's in this oily byproduct. And so here you can see, this is an excerpt from his original paper announcing the discovery of benzene. He says here that my attention was first called to this substance in 1820. Now, eventually, he was commissioned by the Portable Gas Company of London to actually take a look at what is in this oily residue. And so during those times, one of the ways to separate pure substances from mixtures is by a method called fractional distillation. So it's a way of separating pure substances by their boiling points. And so in this method, you would take your mixture and start to slowly heat it up. And every time the temperature hits a boiling point of a certain pure substance, large amounts of it will be converted from liquid to gas, which you can later cool and collect in the form of a liquid. And so that's what Michael Faraday did to this oily product. He noticed that between 176 Fahrenheit and 190 Fahrenheit, large amounts of vapors came out, and he collected them. As a very careful chemist, he went through two ways to try to determine the chemical composition of this pure substance. And here, the most important sentence of the paper and of tonight, he announces the discovery of benzene. He says, I ultimately succeeded in separating a new compound of carbon and hydrogen, which I may by anticipation distinguish as bicarburet of hydrogen. Now that's benzene. The name benzene actually came 10 years after Michael Faraday's discovery, and it was coined by a German chemist named Mr. Leach. From there on, Faraday went on to record the physical properties of benzene, reacted benzene with different compounds to test the reactivity of benzene. And at the very, very end of the paper, the last sentence of the paper, he makes a projection of the impact of his discovery. And this is what he says. It's possible that this substance may furnish the fuel for a lamp, it remaining a fluid at pressure of 2 to 3 atmospheres, but becoming vapor at less pressure shall possess all the advantages of a gas lamp without involving the necessity of high pressure. So now we got better fuel for gas lamp. Now, what Faraday could not have imagined at this point is just how tremendous this discovery was, because the discovery of benzene actually unleashed two major industrial revolutions throughout the Western world in the latter half of the 19th century, the coal tar dye industry and also petroleum industry. Let me go back just 1 second. You can see the sample of Faraday's benzene right here, and it's actually downstairs in the museum on the special display. Around 20 years after Michael Faraday discovered benzene, industrial scale productions of benzene from coal tar became available. And so around this time, many chemists became interested in coal tar research. And the main interest is that you could take a lot of these benzene and benzene-like compounds and try to convert them into useful compounds. And so that's what some of these chemists, like August Hofmann, was very interested in. And so Hofmann actually also found that a lot of these benzene and benzene-like compounds had a special pleasant odor, and so he coined the word aromatic to describe this family of benzene and benzene-like compounds. This is also where the word aromaticity originates from. Now, at this time, August Hoffman had a student named William Henry Perkin. Now, Perkin's project, his research project, was to make quinine out of these aromatic compounds. Quinine is an anti-malarial drug, and so this is what chemists of the time were interested in. We're going to take all these aromatic compounds and see what useful compounds we can make out of it. William Henry Perkin never made quinine. He made something else, and because of that, became an extremely wealthy man. So one day, after finishing his experiments, Perkin was rinsing his glassware with some ethanol when he noticed that some purple solution had appeared. And instead of tossing it away, he tried to dye some cloth with it. He tried some cotton, it dyed purple. He tried some silk, it dyed purple. And then he found that this dye was actually light fast, which means that the dye stuck to the cloth and did not degrade with the exposure to sunlight. And so from that point on, he quit his academic career and he convinced his father to invest in him, and he opened a chemical company, a chemical factory that produced these dyes. So this is actually the first synthetic dye ever made, this Malvine purple color. And this also is very relevant in another sense, that this was actually the first example that fundamental research led to tremendous commercial value. So something like this, a dye like this, a purple color, used to require a lot of stinky and laborious work. So you would have to go and collect thousands and thousands of sea snails, you grind them, and from the glands you get a tiny bit of purple. And so this is part of the reason why purple used to be reserved only for the rich and the powerful people. And it was also said that actually the Catholic bishop and cardinal's robe used to be purple, but eventually they had to change it to red because, in part, because purple was becoming too scarce and too valuable. Now, William Henry Perkin opened his chemical factory for producing these dyes. He also later found other ways to produce dyes that gave colors of reds, blues, greens, browns, and from there, a lot of other chemists and industries followed. And then from there on, the coal tar dye industry basically exploded throughout Europe. Now, one of the reasons why we see the purple color is because of all these aromatic rings that you see here. You see benzene and benzene-like compounds tethered to each other, fused to each other, and this makes it possible for the molecule to absorb in the visible light region. And a molecule like Malvine absorbs light between 500 and 550 nanometers, which is a yellow light. And so based on a basic color theory, the complementary color of yellow is purple. And so if the molecule is absorbing yellow light, what gets bounced back the strongest would be purple. And so that's how you see purple. And so by the same analogy, if you were to make red dye, you have to make a molecule that absorbs in the green. If you want to make blue dye, you make a molecule that absorbs in the orange region. Okay, so as the dye sales went up, this is very important because as the dye sales kept going up, also came with this was a wealth of new chemical knowledge. And chemists started to understand how to do large-scale chemical synthesis, separation, and purification techniques. And this was very instrumental for all the chemical industries, all the chemistry industries that were to come in the 20th century, including pharmaceutical companies, medicinal chemistry, and so on. And this actually became the basis of all the organic chemistry that we find in textbooks today. Now, parallel to this time, what also flourished was the petroleum industry. Now, you may have heard of the name George Bissell. George Bissell is the father of petroleum industry. Now, in the mid-1850s, George Bissell was a young attorney in New York. He visited a friend in Dartmouth, and he came across a sample of rock oil. Now, rock oil is petroleum, but at the time it was called rock oil because it was usually collected by putting large blankets on the surface of rocks to soak up the oil, and then you drain it into a barrel, and the Native Americans would use it as ointments to cure ulcers and rheumatism. So there was some use to it, but quite limited. Now, George Bissell also read a report that says that there are a lot of aromatic compounds in rock oil. And so he had a brilliant idea. He thought that instead of collecting these oils with blankets, we should drill a hole to the source of it, and then we can get lots of it. And so that's what he did. He and his partners founded the Pennsylvania Rock Oil Company, and by 1859, the first oil well was drilled, and from there it set off the whole oil rush. This became even more relevant in the early 20th century when polymerization methods came about. So a polymerization method is a chemical method where you can link small molecules together to make very large molecules. So here I have an example of polystyrene. Styrene is an aromatic compound like benzene with an attached exocyclic double bond. With the polymerization method, you can link many styrenes together and make polystyrene. And the form below is what you see in grocery stores of polystyrene. And so this method made it possible to, from these aromatic molecules, make very useful plastics, adhesives, coatings, packagings, foams, and synthetic fibers. And basically, the petroleum industry became the backbone of our modern day everyday life. Okay, now, parallel to while these two industries flourished across the Western world in the latter half of the 19th century, another type of revolution also was happening in the chemistry world, and that was the birth of structural chemistry. Now, let's say for the most part of the 19th century, first of all, chemists started to believe in atoms. And they also knew about molecules. They also knew that molecules were made up of atoms, but they didn't really think about structure. They thought that as long as you knew the chemical composition, which is how many of what types of atoms you have in a molecule, that's all there is to know of a pure substance. And so during this time, a chemist named Auguste Kekulé came with a very large conceptual leap and suggested that we should care about structure. The way that atoms are linked together in a molecule actually does matter. And from there came the birth of structural chemistry and eventually the proposed structure of benzene. Now here's a picture of Auguste Kekulé. Normally, if you Google his picture, you'll find a picture of an old man. But I tried my best to find a young picture of Auguste Kekulé because this was around the time that he made this conceptual leap and this suggestion to the chemistry community. In 1855, Auguste Kekulé was around the time of what you would imagine an assistant professor today. Now, he published a paper in the summer of 1858, and he said that when atoms come together to form molecules, first of all, carbons can have a combining power of 4. It can connect to 4 other atoms. Also important is that they can be self-linking. So one carbon can connect to another one to make pairs. They can connect to make short chains and to make long chains. And this made it possible for chemists to start to systematically think about structure and think about organic molecules. And it's actually quite interesting to also note that Kekulé actually was originally not trained as a chemist. He was originally trained as an architect. And you can see how his view of what molecules should be, what structures, how important structures are for molecules may have come from his architect training. To show you an example of why structure matters, here I have 2 molecules that have the same chemical composition. So they have the same numbers of carbons, same numbers of hydrogens, same numbers of oxygen, but you can see they are completely different. They have different chemical properties and physical properties. One is a liquid at room temperature, one is a gas at room temperature, and you can see that the way the atoms are linked together and structured are very different. Here you see an excerpt of Auguste Kekulé remembering how his idea of self-linking carbons came about. He was on a bus, dozing off and daydreaming when he started to see atoms dance around, form pairs, form short links, and form longer chains. Now, another very important person to talk about when we talk about structural chemistry is this person, Archibald Cooper, who was a Scottish chemist working in Paris at the time. Now, only a few weeks after Auguste Kekule published his self-linking carbon idea, Archibald Cooper also published a paper with almost the exact same idea. You can see here a translation of his original paper. It says, carbon could enter into chemical union with itself to form long chains. So the same idea, a self-linking carbon. Now, what is very different about Archibald Cooper's paper, though, is that he didn't just describe his idea by text. He actually drew a line to represent chemical union. This is the first time ever that a chemist has drawn a line to represent chemical union between two atoms. And a line is a very powerful representation. Here, let's take a moment to think about how representations guide the way we think. So here I have acetic acid written in the modern form. That's what it looks like. I have Cooper's representation of acetic acid. You'll note that there are extra oxygens in Cooper's representation, and that's because in those days, oxygen was thought to have half the molecular weight as it actually does. So that's where the extra oxygens come from. And there's Kekule's sausage diagram. It's called a sausage diagram because the carbons are represented by 4 lumps, showing a combining power of 4. Now you see, these are very different representations of the same molecule, but they guide chemists to think in very different ways. Kekule's sausage model emphasizes combining power, right? It makes you think about carbon having a combining power of 4, oxygen having a combining power of 2, and hydrogen having a combining power of 1. So it's very meaningful, and it pushes you towards thinking in one direction. If you look at Cooper's representation, the power of a line, when you see a line, you think about directionality, you think about arrangement, and also very interestingly, I think is worth noting here, that Archibald Cooper also was not trained as a chemist initially. He was trained in the classical languages, and he was a linguist. And so you can think about how letters connect to form words, atoms connect to form molecules. And so representations guide how we think, and you see here that once you draw a line, you can start thinking about lines not only connecting 2D, but lines can connect 3D. And so what this idea foreshadowed, what was to come next, was actually stereochemistry and the fact that molecules can be in 3 dimensions. Now you see here, Kekule eventually adopted Cooper's representation of using a line to show the chemical union of atoms by adopting the idea of tetravalency, so the combining power of 4, and adopting this line representation. Kekule eventually came to this proposal of the structure of benzene. And some of you may know his famous story of a snake biting its own tail, which inspired his idea that benzene should have a cyclic structure. Now, very often you will also see this representation of benzene where the hydrogens are omitted for clarity and the carbons are at each of the vertices of the hexagon here. Now, again, this representation is very powerful, even though at the time it was still not complete. There were still a lot of questions surrounding what the structure of benzene should be. But this representation also was very powerful in projecting what could come next, guiding the chemist to think about the next step. Now remember, in 1866, this was before chemists even knew about electrons. Electrons came in 1897, discovered by J.J. Thomson. So this was a pre-electron period. But the fact that you represent benzene in this way, it projected what could come next, and it foreshadowed the ideas of, for example, the 6 aromatic electrons, which came in 1922, suggested by a chemist named Lawrence Crocker. It foreshadows the idea of resonance, the fact that the double bonds in the benzene ring can swap places, and you can actually draw 2 forms that are equivalent to each other. This was later proved by Linus Pauling in 1931 when quantum mechanics came about. Oftentimes, you will also see this representation of benzene with a circle showing 6 electrons delocalized throughout in the ring. Now, this representation of benzene is often associated with the concept of aromaticity, which, if you give it a broad stroke definition, it means a manifestation of electron delocalization in a closed circuit. Now, today, the research field of aromaticity has gone way beyond benzene and what compounds you can make from benzene, but it actually integrates computational tools, spectroscopic methods, and a lot of synthetic creativity. And in a moment, I'll show you some examples of current research topics in aromaticity, but I first want to show you this. Let's take a moment to look at benzene and think about what makes the molecule so special. So these are 3 points that makes it special. Benzene has moderate reactivity, which means you can take this molecule, it's almost like a useful platform where you can stick different useful functional groups on it to make it into different useful molecules. And so here you can see some examples of benzene with functional groups giving you aspirin, paracetamol, TNT, which is an explosive, and hexachlorobenzene, which is a fungicide. And so it's a very useful basic platform where you can stick different functional groups on it and you can make different useful molecules. Second of all, benzene is flat and rigid. Aromatic molecules are flat and they are rigid. So it's basically like a brick, and when you have bricks, you can make molecular architecture out of it. A very good example is your DNA. So your DNA is a double helix, like a twisted staircase, and each of the steps are made of aromatic compounds. Nucleobases are flat and rigid and aromatic compounds. Benzene and aromatic molecules also have free-moving electrons, so the 6 electrons are delocalized throughout in the ring, and when you have free-moving electrons, they can interact with light, and they can have consequences for applications such as electron transport and charge transport. So, roughly speaking, you can separate the 3 main branches of aromaticity research today into these 3 categories. In one category, you can make functional aromatic molecules. In a second branch, you can have reactions that are designed based on the idea of aromaticity. And a third branch of aromaticity research concerns the definition and the concept of aromaticity, which continues to expand. Now here I'll show you some examples of functional aromatic molecules. Because you have a flat and rigid structure, you can actually make all sorts of more elaborate molecular architectures out of it, which can include sheets, hoops, spheres, tubes, and helices. Here's a more specific example to show you. So this is a dimolecule, and again, you see many benzene and benzene-like units fused together, and this is a molecule that you would find in a solar panel, for example. The aromatic molecule absorbs light, and that light can then be converted to electricity. In a second branch of research, chemists realized that the 6 delocalized electrons in benzene are special because they confer a special stability. And so another branch of very active research is to use this idea and design reactions that take advantage of the 6 delocalized electrons. And here you see a textbook example of 6 delocalized electrons in a reaction. A third branch of aromaticity research concerns the definition of aromaticity. Now here, I actually specifically picked some molecules that are aromatic, but they don't look like benzene at all. And so today, the concept of aromaticity actually has evolved far beyond benzene, and a lot of these, you see, an aromatic compound does not have to be planar. It can be a cage shape, it can be spherical, but what unites the idea together is that you have electron delocalization in a closed circuit. And under this branch of research, there's also a lot of computational work on developing methods to quantify or even visualize the effects of aromaticity, as you can see in this example here, a ring current in benzene. Now, in the next few minutes, I would like to share with you one example of a modern research in the field of aromaticity from my own research group, where we use computational methods to look at DNA and to show that a very important photoprotection mechanism of your DNA actually is largely related to the effects of aromaticity. Now here you see an example of here you see an animated clip of your DNA, a double helix structure with a twisted staircase. Now again, each of the steps of that staircase is a pair of aromatic compounds. It can be an adenine-thymine pair paired together by a hydrogen bonding, or it can be a cytosine-guanine pair paired together by hydrogen bonding. Now, what happens when your DNA is exposed to UV light is that the aromatic compounds absorb the UV light, and now they become very reactive. Now, what can happen when they're very reactive is that they can actually undergo reactions that eventually could lead to mutation or some bad reactions. And so here's an example of that. This is one of the reactions that could happen. If you have two thymine pairs stacked on top of each other, upon exposure to light, they can form bonds to each other, and that creates a kink in your DNA, and that is one form of mutation. Now, what your DNA does is something very clever. It directs the energy and does a different sort of reaction, and this is called a proton-coupled electron transfer reaction. And in my research group, we used many of the computational tools developed today to quantify aromaticity, and we find that this alternative photoprotection mechanism is largely driven by the effects of aromaticity. Now, if you take a look at the time scale of the two reactions here, you see that the dimerization reaction happens in 1 picosecond, so that's 10 to the minus 12 seconds. This protection mechanism overall takes 10 picoseconds, but the first step, which is an electron transfer, takes only 0.1 picoseconds, and that competes for harmful reactions that could happen, and this is driven, we find that this is driven in part by the effects of aromaticity. Now, coming towards the last part of the talk, I want to tell you the story of Kathleen Lonsdale. So Kathleen Lonsdale is the first chemist who put a nail in the coffin and proved the structure of benzene using X-ray crystallography. To give you a context of where we are in history, we are now about 100 years after Michael Faraday discovered benzene. So we're way past the Napoleon Wars. This is actually around the time when Titanic set sail for New York. Now, before I go into Kathleen Lonsdale's story, I want to just take one step back and let's look at Kekulé's benzene structure again. The emphasis that I want to make here is that Kekulé's proposed benzene structure could always only be inferred in 1866, because first of all, there was no knowledge of electrons, and second of all, there was no X-ray technique. And so this structure can only be inferred by the reactions that benzene undergoes and the products that you get from these reactions. And so the missing steps had to develop before the structure of benzene could be proved. Kathleen Lonsdale proved the structure. She resolved the structure of hexamethylbenzene using X-ray crystallography in 1928, and in 1931, hexachlorobenzene. And so this is a X-ray spectrometer that she might have used at the time. And again, there's also a model right down, sorry, not a model, the actual thing downstairs in the museum. So before you leave, make sure to take a look at it. So this is an X-ray spectrometer of the time that Kathleen Lonsdale would have used for her experiments. Now, to take an X-ray crystallography, first you need a crystal. Now, how do you get a crystal? So you get a solution of your compound, and you start to slowly lower the temperature. Now, when you very slowly lower the temperature, what happens is that the molecules floating around in the solution come together, and they slowly form a regular pattern in the form of a solid, and that solid is called a crystal. And when you do an X-ray crystallography, so this is a modern rendering of a benzene solid in a crystal form. So you see that the molecules are arranged in a regular pattern in the form of a solid. When you do an X-ray crystallography, you shoot an X-ray at the crystal, and the X-ray interacts with the electron cloud around the atoms, and they become scattered. But because the atoms are arranged in a very regular way, the scattered patterns, the scattering becomes a regular pattern, which you can capture on a detector. And it looks like something like this. This is not for benzene, this is for zinc sulfide. But this is what an X-ray diffraction pattern looks like. Very regular, with some dark spots, some light spots. Now, to solve an X-ray crystal structure, you need two things. First, you need to be good at math, as you can see in the circle on the right. So you'll have to relate the space groups, or relate the symmetry of the crystals to the diffraction amplitude, so how dark the spots are. So you must be good at math. Number two, you must have good luck, because the first step of resolving an X-ray crystal structure is that you have to guess the answer first. So you guess the answer, and you predict what the diffraction amplitudes should be, and then you see if it matches what you find in the experiment. If it doesn't match, then you guess again, and then you repeat that until you get to a very close answer. And so you can imagine that this is somewhat limiting, because that makes it possible only for very simple X-ray structures to be resolved. Now, Kathleen Lonsdale applied a very creative solution for solving the crystal structure of benzene and for many organic molecules. She was a pioneer in applying what is called a Fourier decomposition method to solve X-ray crystal structures. And so what she realized is that when you get a complicated diffraction pattern like this, it can actually be mathematically decomposed into simpler signals that gives you information about electron density, which is what you see in this circle over here. And if you want to understand what a Fourier decomposition method is basically you can think of having a very messy sound wave, like what I have up there in the slide, and then you can decompose it mathematically to a sum of simpler waves. And this is the method that Kathleen Lonsdale used to resolve X-ray crystal structures. And so this was very important because by applying the Fourier decomposition method to X-ray crystallography, this allowed much more complicated structures to be resolved, and this was the reason why in the latter half of the 20th century, complicated structures like penicillin, like vitamin B12, like proteins and DNA and RNA could be resolved, and today we still use this method. Now, as we've seen in the story of Michael Faraday, very often behind a hero or a heroine, there is often an unsung hero. And I think in many ways, that person for Kathleen Lonsdale was her husband, Thomas Lonsdale, who was a physics professor at the University of Leeds. And he relentlessly supported Kathleen Lonsdale's career and her science. Kathleen Lonsdale went on to be one of the two women to be elected a Fellow of the Royal Society, and she was also the first woman to stand here and give a Christmas lecture. And it was an event that documented her legacy in crystallography, as well as her as a pioneering woman in science. Now, coming to the very end of my talk, I want to say that there are a lot of lessons that you can take away from learning about the stories of our scientific heroes. How did Faraday, the son of a blacksmith, a bookbinder's apprentice, an assistant at the Royal Institution, go on to become one of the most celebrated scientists in history? While preparing for this talk, which is actually a very long time, something jumped out at me from Faraday's story, and I think it's the many form of kindness that Michael Faraday experienced throughout his childhood and also throughout his path on science. And this resonated with me very much because that is also what I have experienced on my path in science. I think a lot of times when you think about scientific discovery, you think about intelligence, you think about creativity and determination, but I think what the story tells us here is that it's also about the people and about the kindness of the people that give you opportunities, people that support you, sometimes people that give you 4 tickets. And so here you see that this act of kindness, you see the imprints of these acts of kindness in Faraday's character. Faraday was known to be a very humble man and a very empathetic character. He was very well liked. In 1825, the same year that he discovered benzene, he created the Christmas lectures, the Discourse lectures, as a way to share his love for science and for discovery with the public. He was known to be a very charismatic speaker, very engaging. Despite his brilliance, he was offered a knighthood, but he refused because he said he prefers to remain plain Michael Faraday to the very last. And when reflecting on his childhood, he says that he always feels a tenderness for the newspaper boys because he also once carried newspapers himself. And with that, I hope you enjoyed the lecture tonight.